back, everybody. So as I had mentioned here, quick update on things. We'd missed Monday's lecture, and I was looking at the schedule of planned lectures, and what I decided to do, rather than have a supplemental lecture kind of in the middle of this, is finish what I intended to put in the supplemental lecture, and then I'll reserve the right later, if I think it's necessary to get what I want to cover, to upload a supplemental lecture, which will happen either over the break or after. I know for some of my other classes I was doing it over the break, but I think actually for you all I will save it until later, because later is when there's definitely some stuff that I would want to relegate to a supplemental lecture, rather than go over it at length, kind of in one of the main lectures. So anyway, I wanted to finish up talking about Archimedes. So last time I had mentioned a few things. So one thing I'd mentioned by flipping through this. I have this collection of the works of Archimedes, and I was flipping through it on camera and showed a couple of things that Archimedes did. So one was I showed that by inscribing a 96 or a regular 96 gun in a circle, he obtained this result, right? So what are some of the things that he did? Just quick refresher. He had attained this approximation for pi, that said that pi is greater than 3 and 1071sts, but less than 3 and 1/7. Okay, so he obtained this approximation for pi. Perhaps not surprisingly, he proved that the area of a circle is pi r squared, right, where r is the radius. Okay, this finishes work that was originally set in motion 200 years prior to Archimedes, right? So remember, going all the way back to Antiphon, right, who was the first to come up with this idea of inscribing regular polygons of larger and larger size. The idea that Antiphon came up with, and I can't remember exactly the degree to which Antiphon did it, but Eudoxus picked up there and did this, proved this fact that Euclid included in the elements, that inscribing this regular 2 to the n-gon gave you this nice bound on the area. So Archimedes is clearly using that fact, or at least the ideas behind that fact. So this finished the work originally begun by Antiphon. And Eudoxus. Okay, remember, and the best that was done before Archimedes was proving that the area was proportional to the square on the diameter of the circle, right? So this shows exactly what the proportionality constant is in that case, right? Okay. All right, so this is a big deal, and I'm going to go over exactly how he did this in a second, or at least the process that led him through this, just as this is kind of a nice example to show his way of thinking here. Because this is actually really nice. So what's some other things that he did? As I showed last time, let me dig up my copy of Archimedes' Quadrature of the Parabola. As I showed last time, we have this absolutely amazing work due to Archimedes. So look at that, right? This looks like something that could come straight out of a calc textbook, right? This is something like straight out of a Calc 1 textbook, because essentially this is computing areas of trapezoids in this way, and using these the sums of these areas to compute the actual area underneath this part of a parabola. As I mentioned last time, the idea was if I have a parabola and I have this chord here, right? If I have this segment that is connecting the parabola, being able to compute the area of that parabola as the area of a particular triangle drawn in here in this way. And so actually he does this, or at least as proportional to the area of this particular triangle. And in fact, that proportionality constant is 4/3 here. Okay, so this is like an absolutely amazing feat. This is something that is not, nothing came close to this in terms of sophistication until the 1600s, basically, until Newton and Leibniz and the discovery of calculus. So he computed the area under a parabola. Now, he didn't do this totally generally, but he was able to compute the area under a portion of a parabola as an area of a particular triangle, and these methods were general enough that basically this finished the case of parabolas and computing areas underneath them. So with a little bit of modification, this basically does it all. Okay, so what else did he do? He, as I said, and I'm going to, I know I've been promising the large info dump of a long list of references, so I'm still working on it because it's going to be absolutely massive. And included in that is this thing I'd mentioned before, where a lot of these works were actually unknown in antiquity. They were basically lost soon after Archimedes lived. Some of these works were lost, and they were only discovered much, much later. So an example of that is a work that Archimedes did called the Stomachion, which is basically a combinatorial puzzle. So it is one of the earliest, probably the earliest example of combinatorics or combinatorial arguments in math. So the Stomachion is a combinatorial puzzle. I don't believe that this textbook actually includes reference to it, because the textbook was published before this was fully known, that this is what it contained, I believe. I'm not totally sure about that, but that seems reasonable because I believe this textbook was published in the mid-90s, and some of this stuff wasn't actually fully worked out until the early 2000s. So this was basically the problem of given a square broken into some number of pieces in a particular way. So this is not going to be strictly like exactly the question as it's involved. This is just like an example. Okay, so suppose I have a square that's split up in some way like a puzzle. The question is, depending on the configuration of this puzzle in question, can I compute the total number of ways this square can be broken up and reassembled, and I still get a square? Right. So this sort of argument, this is something that Archimedes addressed in antiquity. These are just the mathematical achievements, and this is absolutely not an exhaustive list. It would take me far too long to exhaustively treat Archimedes' things. Let me mention a couple of the historical facts again. As I had mentioned previously, Archimedes was presumably educated or had some connection to Alexandria. He, as I'll give an example of in a little bit, he had correspondence with mathematicians in Alexandria. He would send them results. He would sometimes get annoyed when he would send them a result of something that he had proven, and they would respond back saying, "Oh yeah, what a coincidence! Like we actually also just proved this." And he felt like that was happening maybe a little bit too frequently, and so he would sometimes intentionally include false results to see if they would, mirror his claims, so that he would know that they were clearly trying to steal his achievements. And he would also pose them problems, probably that he knew they had absolutely no hope of being able to solve. So I'll give an example of one of those at the end. It's called Archimedes' cattle problem. Archimedes, I'd already described maybe some of the eccentricities about him. He was known to be extremely involved in his computations, and that's pretty much all that he cared about. But Archimedes is known not just for his contributions to math, but I already mentioned his contribution to physics in the form of the Archimedean principle, being able to actually figure out the composition of, say, a crown, right? What type of metal, what exactly are the ratios of metal used, and its composition by, submerging it into some basin of water, right? Something that the density of. So the idea is that he was also extremely gifted in engineering. So there's the Archimedean Screw that you might have heard of. There's the Claw of Archimedes that you might have heard of, which was built supposedly for the defense of Syracuse, and that could apparently lift ships out of the water and smash them down back into the water and destroying them. There's the Archimedes Death Ray, or the Archimedes Heat Ray, which were these giant mirrors that were constructed in a way to supposedly start fires on ships that were sitting stationary, besieging the city, right, blockading the city. So some of those things have been tested, like the Archimedes Heat Ray, and have found to maybe they wouldn't have been that super effective. But he was certainly known throughout the ancient world for those inventions, more known for those than he was his mathematics, because, well, one, his mathematics was kind of so far ahead of the time that it would have required another very astute mind to even recognize them. And also his works weren't as widely read, mostly because it just so happens a lot of them were lost at really inopportune times, and so they weren't widely read, forgetting about the fact that there wasn't a huge audience that could have even been that receptive to them. He was just that far ahead of everyone. So he also probably had something to do with the Antikythera mechanism. So the Antikythera mechanism, if you haven't heard of that, so here's the word that I'm saying. So the Antikythera mechanism, named because it was recovered off Greek island in Mediterranean named Antikythera, I think. And the Antikythera mechanism was an extremely advanced mechanical system that is believed to have been used in a manual analog computer of a sense. It was this hand-cranked machine that produced predictions about future astronomical observations, eclipses, and the motions of the planets. So there are a couple of ancient accounts of this thing in action. In fact, famous Roman writer, and I can't remember off the top of my head if it was Cato or if it was Cicero, I can't remember. I'll include that in the info dump. Actually gave an account, an ancient account of one of these mechanisms in work. Supposedly, one of these mechanisms, or something very close to this, was actually taken as Marcellus's only piece of personal loot when Syracuse fell during the Second Punic War. And so The Antikythera mechanism was this extremely advanced mechanical piece of equipment that either originated with Archimedes, or it was certainly something that apparently the ancients ascribed to Archimedes, or at least he was responsible for maybe propagating the technology further. So it's pretty amazing, actually. This is a bit of lost technology, and this wasn't known until relatively recently that this thing even existed. So so he was well known for these things. I have tried to list, some of the major mathematical accomplishments of Archimedes. This pales in comparison to all of the things that he did, but I can't. It would take me forever to go into detail on absolutely everything that he did. I didn't actually finish my my rant last time on why I think Archimedes is the greatest of all time, and it's pretty, objectively true, I'll say. Totally not biased because he's my favorite mathematician, but the reason that I say this is it's a question of relative ability, right? So I mentioned last time that it's not fair to compare like the abilities of a modern mathematician who's had, many, many years of education in math that was unknown to the ancients and unknown even to, the greats of just like 200 years ago. So it's unfair, right, to compare like just pure knowledge, right? That doesn't make any sense. So then what makes sense is to compare your ability, right, relative to your peers at the time, right? So when we talk about Newton and how great Newton was mathematically, it makes sense to compare Newton to others that were active in math at the same time. So same thing with Archimedes. And this is where Archimedes really shines because, as we will see, as this lecture continues, right, I'm going right into the post-Archimedes world mathematically. And as we will see, there are huge gaps, and they're not really filled. In fact, there's not really a mathematician on the level of Archimedes until Newton and Leibniz and the discovery of calculus. So, this is thousands of years of a gap. And Archimedes was so far advanced of, what came immediately before him as well. It's pretty clear that he is a massive aberration. He is like such a ridiculous outlier in mathematical ability, and that's why he's frequently cited as, one of the greatest mathematicians of all time, because he's just such a ridiculous outlier in terms of ability that it's actually kind of silly to consider, to try to consider it like that. So, basically the argument is that even as great as Newton was as a mathematician, he had peers that were, roughly on the same level. The Bernoullis, Leibniz, we use Leibniz's notation anyway. And then, not even a few decades later, you have Euler. It's pretty easy to argue that Euler is a greater mathematician than Newton. By a number of metrics. Now you could say that, and that's only a few decades later. It's only a few decades after Newton's death. You have Euler, being one of the greatest mathematicians ever. That's really close to Newton. Now you could say, well, Newton was writing during the Enlightenment, so it's natural that the progress would be really, really quick. But it's still, ridiculous to think of the hole that would be left. Like if you removed Archimedes out of the ancient world, then there would just be this massive, there wouldn't be this spike in, mathematical achievement that was done where Archimedes gets so close to calculus, right? I showed how in this quadrature of the parabola, right, computing the area under a parabola, he's essentially doing calculus, right? He's essentially integrating. He is so close to developing calculus. And without Archimedes, it's not that Archimedes was that influential, because he wasn't that widely read, and there weren't really the minds that were able to even properly, take in what it was he was doing. Even so, removing Archimedes from the historical record is removing a giant spike, right? Whereas like removing a Newton, or a Bernoulli or a Gauss, while they had achieved things like that were amazing, it wouldn't leave the same kind of hole as removing Archimedes. So that's basically my argument, that Archimedes is the greatest mathematician ever. Maybe you don't totally agree with that. Maybe people that are big fans of Newton or Euler would disagree, but that's basically my argument. So, as I said, Archimedes lived during the Second Punic War. I could spend all day talking to you about the Second Punic War. It's basically my favorite time period and event in all of history, because it's got my favorite mathematician Archimedes and my favorite historical figure Hannibal Barca. So it's pretty hard not to love. Like I said, the textbook actually offended me when it said, "Who today would know of Marcellus if it weren't for Archimedes?" Marcellus was the Roman general that led the siege of Syracuse. So Archimedes lived in Syracuse. This was during a very tumultuous period of the Mediterranean. I won't totally get into it, but basically Rome and Carthage were vying for dominance. In the First Punic War, Rome had won after developing its own navy, which Carthage had previously completely dominated the naval scene in the Mediterranean. So First Punic War was won by Rome. Carthage recouped its losses by holding on to alliances in Sicily. So they were allied with the king of Syracuse, which was King Hero. And they had also picked up a bunch of colonies in what's now Spain. So, for instance, Barcelona, right, famously founded by the Barcid family, Hannibal and Hamilcar, his father. And so anyway, the Second Punic War breaks out. Hannibal besieges and captures the Roman city, a Roman allied city in Spain. Saguntum is the city that was captured, and then after that, famously marches over the Alps, invades Italy, and stays there for about 16 years. Inflicting a ton of losses. I think at one point, in like 3 campaign seasons, Hannibal had killed something like 30% of the adult male population of Rome. Anyway, so it was a big deal. It was like Rome's finest hour, basically, in terms of the Roman Republic. Anyway, it was like the Roman Republic's finest hour in terms of showing how resilient its system was. So Syracuse was allied with Carthage. Carthage was on the losing side eventually, and so by 212 BC, the tides had definitely turned. Syracuse had been besieged by Marcellus, who was the best general on the Roman side. Not that well known to a lot of pop history people, but Marcellus is one of the best, or was the best Roman general in that war. And Marcellus had specifically given instructions, as it was clear that Syracuse was about to be taken. He had specifically given instructions to not hurt Archimedes. So Archimedes was not to be harmed. And so when the Romans were capturing the city, some random Roman soldier comes upon Archimedes, who is, of course, completely engrossed by some diagram he's drawn in the sand. He's drawn a bunch of circles, and his last words supposedly were, "I beg you, please don't touch my circles." And then he was killed, and Marcellus was apparently really, really upset by this. And the only 2 pieces of loot that Marcellus took from the siege of Syracuse were 2 of these Antikythera mechanisms, basically these models of the solar system, basically, that could be hand cranked to show the relative motion of the heavenly bodies. And so one of them he deposited in a temple in Rome, and that is the one that is described by, I believe it's Cicero. I'd have to look. So that's the one that's described later. That's like the only known, I think, ancient description of this device. And then the other one he apparently took as his only personal loot from that campaign, and that's how much respect he had for Archimedes. So anyway, that is the story of Archimedes and how he met his end in 212 BC during the capture of Syracuse. So I wanted to go over Archimedes' reasoning behind this proof that the area of a circle is given by this famous formula pi r squared. Okay, so how did he prove this? So let me bring this closer and zoom in. Okay, and so here are the assumptions, right? Circles and circle segments have areas. Okay, I don't think that's anything anyone's going to argue with. Secondly, the area of a set of pairwise disjoint triangles and circle segments equals the sum of the areas of those triangles and circle segments. Thus, if we dissect a circle into triangles and circle segments, the area of the circle is the sum of the areas of the triangles and circle segments into which it has been dissected. Also, the area of the circle is greater than the sum of the areas of any proper subset of those triangles and circle segments. That is very wordy, but that says the intuitively obvious statement that if we take a region and we split that region, right? So we take a 2D region, we split that region into a bunch of pieces, and we take those pieces and we think about how we could, motion is not mentioned, but the assumption here really is that if I think about taking these pieces and I could even move them around, I could rotate them, I could flip them, I could do those things, and that's not going to affect the area, right? So certainly just this act of splitting them into the area is not going to affect the area. This is a statement that a one-dimensional region has area 0, right? So I'm not adding anything. Note perimeter, I can't do this with perimeter, right? If you take a rectangle and you break it into a bunch of pieces, and you think about counting the perimeter of those new pieces, you've added perimeter, right? So perimeter does not satisfy this, but area does, okay? Area does. So Euclid, of course, used this a lot, where he would take a figure, like a triangle, and he would associate that triangle with its area. So when he would talk about area, he was talking about the triangle and vice versa, okay? And in fact, he did this when he proved the Pythagorean theorem, his first proof of the Pythagorean theorem. Okay, so 3, given any circle, there is a straight line segment which is longer than the perimeter of any polygon inscribed in the circle and shorter than the perimeter of any polygon circumscribing the circle. This is the circumference of the circle. Okay. So the first person to give the name pi to the circumference of the circle with unit diameter was not Archimedes. It was William Jones in 1706. Okay, so pi was not the symbol that Archimedes was using. But anyway, so of course it's the same quantity that's being described here. Okay, next, this is a property that if you've had Math 310, Math 410, or any of the proof math classes before, you will have seen number 4 called something specific. So given any areas E and F, there is a natural number m such that m times E is greater than F. This is called the Archimedean principle, okay? And so this is the first context in which it shows up. Now, it's called the Axiom Archimedes, but as it's pointed out here, this did show up in Euclid's Elements, and also it showed up in Aristotle as well. But it's called the Archimedean principle because this is kind of like the most famous first instance of it being used, okay? So this is like universally called the Archimedean principle. Everybody calls it that when referencing it. The next assumption, a regular 2 to the n gon inscribed in a circle takes up more than 1 minus 1 over 2 to the n minus 1 of its area. This is that fact that was stated in the Elements, but it was actually proven by Eudoxus. So a regular 2 to the n gon circumscribed about a circle has an area less than 1 plus 1 over 2 to the n minus 2 of that circle. This is also the thing that Archimedes used by inscribing a regular 96 gon. He used this to come up with his approximation for pi. Okay. Number 6, the area of a circle is proportional to its diameter squared. Again, this is straight out of Euclid's Elements. This was the extent of the knowledge about the area of a circle before Archimedes proceeded like this. Okay, so using these assumptions in this baseline, how did Archimedes come up with the area of a circle? Well, he did this by contradiction. So two contradictions, so A and B here. So A, suppose that the circle has area greater than that of a right triangle T whose legs equal the radius and circumference of the circle. Okay, so what is the area of that right triangle whose legs equal the radius and circumference of the circle? Well, that right triangle has area pi r squared. Okay. Now, why is this going to be a contradiction? So by number 4 and 5 above, you can find a natural number n such that the circle area minus the inscribed regular 2 to the n-gon area is less than the circle area minus the area of t. Okay. Thus, the area of t must be less than the 2 to the n-gon area. Okay. Now, if AB is a side of the inscribed regular 2 to the n-gon, and ON is a perpendicular from the center O of the circle to AB, where n's the midpoint of AB, then ON is less than the radius of the circle. Okay, think about that for a second. Using 3, this assumption over here, okay, using 3, we have that the 2 to the n-gon area is 2 to the n times 1/2 AB times ON. This is just the standard area of a triangle, right? So this is 1/2 times 2 to the n AB times ON. So this is 1/2 the, remember we've set up T so that this is the circumference times the radius, right? That's the area of T, all right? But that can't be. I've said that the area of T is less than 2 to the 2 to the n-gon area, but then this just shows that the 2 to the n-gon area is less than the area of T. That can't happen, right? So A cannot be true. So the circle cannot have area greater than that of the right triangle T having that area exactly as we think. So then the second contradiction that Archimedes derives is suppose the circle has area that's less than T. Well, by 4 and 5 again, there's a natural number n such that the area of T is greater than the circumscribed regular 2 to the n-gon area. However, if AB is the side of the circumscribing regular 2 to the n-gon, then again by this property 3, the 2 to the n-gon area is this 2 to the n times 1/2 AB times the circle radius, but that's 1/2, or that's greater, so that's greater than 1/2 circumference times radius, which is the area of T. So I've shown the opposite inclusion. Now, this could have been done in a slightly more efficient way. You could actually have done these contradictions basically at the same time to get what the result is. But if my circle can't have area greater than that of the right triangle described in that way, but it also can't have area less than that right triangle described in that way, by a fact called trichotomy that Archimedes is implicitly using here, there's only one other option, right? If the area of my circle can't be greater than the area of T, and it also can't be less than the area of T, then it has to be equal to the area of T. But the area of T is pi r squared. So the area of the circle is pi r squared. Okay. So this is an example of Archimedes' type of reasoning. And so this was the original proof that the area of a circle is pi r squared. Okay, so one more fact about Archimedes. As I had mentioned earlier, Archimedes was in constant correspondence with mathematicians in Alexandria. Unfortunately, a lot of these letters were lost until much later. Some of them were translated by Arab translators. Some of Archimedes' other works were translated by Arab translators. Well, I should say Arab or Islamic translators more generally, because there's a lot of Persians in there as well. So Muslim translators preserved some of Archimedes' work. Some others were lost until much more recently. That's where the Archimedes palimpsest comes in. But it is known, it's well attested, that he was in contact with mathematicians in Alexandria, and as I mentioned, he would sometimes show them his most recent results, and they would reply back with, "Oh yeah, that's funny that you mentioned that, because we also just figured out this fact." And so he would get slightly annoyed with them and would send them false results, sometimes kind of peppered in his his true results to see if they would, if they would recognize that they were false, or if they would try to claim that, oh yeah, we also came to this false conclusion, right, that you just made up. He would also issue them challenges. So one example of a challenge like that is called Archimedes' cattle problem. Now I'm not going to write out Archimedes' cattle problem. I'm going to give you the description coming straight from the textbook. So what is the Archimedes cattle problem? Okay, so this was posed as a challenge to Alexandrian mathematicians. So the cattle problem is this. The sun god has a herd of cattle consisting of W white bulls, G gray bulls, B brown bulls, and S spotted bulls, as well as W prime, G prime, B prime, and S prime, respectively, cows of the matching colors. What was the total number of bulls and cows if S, G, and B, or if all these things satisfy this relationship here, together with these other relationships, and the fact that W plus G is a square, and B plus S is a triangular number. Okay. Now, these types of questions, where you are restricting your attention to positive integer solutions here, since you're clearly looking for a total number of bulls and cows, right? These are mundane objects, so I'm going to assume that I'm talking about positive integer solutions. These are example of equations known as Deophantine equations. Okay, as we'll see, Diaphantes came later, much longer after Archimedes, but these are typically called Deophantine equations, even though Archimedes is one of the first people known to have posed questions like this. And so it turns out that this is pretty complicated, and using some algebra and some substitutions here, we can see that solving this cattle problem, right? So here's a bunch of different relations involving these things, and then we have additional relations from W plus G being a square. It turns out that you can transform Archimedes' cattle problem into finding an integer solution of the equation 2 to the n plus 1 squared minus 8 times 2471 times 957 times 4657 squared times t squared is equal to 1. Now this is a complicated equation to solve. Obviously, as it says here, the mathematicians at Alexandria could not solve the problem. It wasn't solved until 1965. The answer was 206,545 digits long. Okay. Now, whether Archimedes actually already knew, had maybe worked backwards and already knew the answer, is debatable. That's a pretty long number, but it's not, not outside the realm of possibilities that Archimedes knew this. Archimedes, maybe one more thing I'll fit in before really moving on finally. There was a work of Archimedes called the Sand Reckoner, where he was supposedly given the problem of counting all of the sand in the world, like every grain of sand, like in the world, or either that could fill the universe. There was I can't remember the exact problem statement, but it was basically a problem of counting objects that there were like clearly an absurd amount of. And so in order to do this, Archimedes basically developed kind of an analog of scientific notation using what we would call exponents to denote these large numbers. And he came up with an estimate for how much sand it would take to fill the universe as well, which you can have a look at. So the name of that paper is called the Sand Reckoner. It's impossible for me to really fully credit Archimedes here in the way he deserves, but unfortunately I think it's time to move on from Archimedes. And as we'll see, not all of my ranting was completely out of nowhere here. The reason was to imbue in you a sense of what is to come, and that is after Archimedes, we are going to move very fast for a while. So as you will see, our next topic is Alexandrian Mathematics from 200 BC, right, which is a little bit after Archimedes died, to 500 AD. And as it turns out, the inclusion of 200 BC is really due to like a single person, Hipparchus. Outside of Hipparchus, we can immediately jump over 200 years firmly into AD territory. And actually, in this entire lot of mathematicians, there's really only like two-ish. There's like three in this entire span that are kind of the big names. The others had respectable accomplishments, but there's three that are kind of the big names. So what are some of the mathematicians that did work in this time period? So there's Hipparchus. So Hipparchus of Nicaea. So Hipparchus was born in about 180 BC. So born about 30 years after Archimedes' death. So I'll mention all the things that these people achieved. Heron of Alexandria was known mostly for a single formula that's very nice, that may actually be due to Archimedes anyway. So he was active about 60 AD. Okay. There's Menelaus of Alexandria, who is active about 100 AD. Okay. There's Ptolemy of Alexandria, not to be confused with the earlier Ptolemaic rulers of Alexandria. He lived in Roman Alexandria. So he died in 168 AD. As a mathematician, there's some things to say about Ptolemy, but he is undoubtedly more known. You've come across his name undoubtedly if you've studied anything about the history of science at all, because it was the Ptolemaic model of the universe that was, the big contentious subject, right, of Copernicus and Galileo, ultimately resolved by Kepler and others. It was this Ptolemaic model of the universe that was under attack, and this was due to Ptolemy. So he was well known as an astronomer. And that's primarily probably where you've heard of him, but I'm going to talk mostly about his mathematical accomplishments. There's Diophantus that I mentioned previously, was active approximately 250 AD. Diophantus was known for his analysis of what are called Deophantine Equations. So these are, that is still the title of this subject. There's an entire field of mathematics, number theory, called Deophantine Equations. So some of the more famous problems involve Deophantine Equations. This is a huge topic of research, and this was named after Diophantus. We saw that Archimedes had an example of a Deophantine equation, but Diophantus did this almost exclusively. This was basically his thing. There's Pappas of Alexandria, very important in geometry. So Pappas was active about 320 AD. These are the most significant contributors to mathematics during this time. Of these, the big ones are, so Hipparchus did a lot, actually. Hipparchus was basically the founder of trigonometry, and I'll mention that next time. But so Hipparchus did quite a lot here. The big names here that deserve the most mention are Diaphantes and Pappas. So they did kind of the most. Ptolemy did a lot, obviously, for science in general. His mathematical contributions were not as impactful. Diaphantes and Pappas, though, were. Pappas was probably the last great mathematician before Newton. So Pappas was like the end of the line. Now, none of these mathematicians are on the same level as Archimedes. Probably not, relatively speaking, on the same level as like Eudoxus before Archimedes, but nonetheless, these are significant mathematicians that did significant things in this time stretch. But this pretty much ends it. Pappas is the last the last heavy hitter here. So there are some lesser known mathematicians that did make contributions, but not at the same level as these. So some of those, there's Nicomachus. I actually have some of his works as well in that same tome from which I showed you, Euclid and Archimedes. So there's Nicomachus of Garasa. Okay, so Nicomachus of Garasa was active about 100 AD. There was Hypatia, famous female mathematician who was famously killed in 415 AD during was a riot. I think they were like anti-pagan riots or something. The circumstances surrounding her death aren't totally clear. I'll talk more about that when I mention her. There's Proclass, which you have heard before because his commentary on Euclid's Elements and earlier Greek mathematicians was well known. So he was probably, would say, his greatest accomplishment was his well-known commentaries on earlier Greek mathematics. So this is 410 to 485 AD, and Boethius, which was active from 475 to 524. Well, I think he was born in 475 and died in 524. Okay. All right, so these are the lesser players in this time period. As you can see, most of the lesser players are congregating towards the end of this window, 500 AD, because things are definitely winding down here. And as we're about to see, literally in the span of a couple of chapters, we are going to go right from Archimedes, who died in about 212 or died in 212 BC, to discussing, this 700-year gap, plus we're going to go from here into the Dark Ages, where almost nothing is happening in Europe in mathematics. So we're going to use that opportunity to talk about Indian and Chinese mathematics, and then the Muslim mathematics that was done in that Dark Ages gap. And then we will basically be to the stuff right before the Enlightenment. Right, the Renaissance mathematics is taking place in the 1400s, and then ultimately we're going to go into Newton, Leibniz, discovery of calculus, these things. But notice, right, in the span of just a couple of chapters, we're going to go all the way from Archimedes to the 1400s. Right, we're going to jump 1600 years in the same time that it took us to discuss like 200 years of Greek mathematics. So that is the gap that is coming, right? And you can see from this rundown of how these things are winding down and how quickly it is approaching a time when almost no mathematical progress was made whatsoever for a long time. There were some shining beacons of light in the night, but not a whole lot of progress was made for a very long period of time. And so, at least mathematically, right, there was technological progress in a lot of ways, but mathematically there was very little progress happening at all. So anyway, I think that's it for today. I know I keep saying this, but I'll be making some gigantic posts soon. Those of you that email me asking about whether or not you'd missed some homework assignment, you haven't missed anything. I haven't posted the second homework yet. I'm gonna post second homework soon before spring break, and then after spring break. So your second homework won't be due until after spring break. When you come back from spring break, we're gonna have that week. We'll have our first midterm. It will be a mixed. It will be mixed between writing and some computation type stuff. It'll be kind of similar in spirit to the homework, but I may have some questions that are like longer essay type questions as part of your exam. Your exam is not going to be timed, as I mentioned. I will post it just like I post your homework, and you'll have some number of days to do it, to work on it. You'll have a while. You'll have at least a week to work on it because it's going to have writing bits, so I'm not going to have a quick turnaround on it. But anyway, I'll keep you all updated with that. So anyway, I will see you all on Friday.